Hi, it's time for another math easy solution. Today I'm going to discuss further into improper integrals and now go over example 9. And this example is a pretty interesting one. This is basically, this example states, show that the following integral is convergent. Now this example is really interesting because this particular function, this integral from 0 to infinity of e to the power of negative x squared, the thing with this function is, as discussed in my earlier video titled Can We Integrate All Continuous Functions, and you can see that in the video links below in the description, this function has no direct solution because it is not an elementary function. So basically there's no way of directly solving this in terms of functions we know, such as power functions, polynomials, etc. So anyways, make sure you learn more about elementary functions in my earlier video. So if we can't integrate this properly or directly, what we can do is compare the integrand, which is the function inside the integral, e to the power of negative x squared, with one that we know how to integrate, which is this one right here, y equals e to the power of negative x. This one, we could take the integral of this function pretty easily. So if we compare the two from this interval, so at x equals to 0, I just wanted to point out, for both of these, e to the negative x squared, this becomes, well, e to the 0 squared, 0, that's still 0, e to the power of 0, that's just going to be equal to 1. And same with this function here, e to the negative x, that's just equals to e to the 0, which equals to 1, no, negative 0. So the other one other value I want to get is the e to the x equals to 1. So in this case we have e to the negative x squared. This becomes e to the negative 1 squared, which again, this 1 squared is just 1. So this equals 2, well, e to the negative 1, or 1 over e. And then similarly for this case right here, e to the negative x, this is just equals to e to the negative 1, which equals to 1 over e. So at these 2 points, both of these values are the same. And both of these functions, as you plug in, let's say, number really large, you're going to be dividing by, well, a big number. They're both going to be going to 0. But what I want to show is just basically just how the function looks like. So let's just look for this range initially from x equals to, let's go x is less than 1 but greater than 0. So at this point, this is just so that when we graph it, it'll be easy to understand. So between 0 and 1, what we actually have is the function e to the 1 divided by x squared. This one is just this one. Just flip it over. Put it bottom and make it positive. Same thing, this function here is greater than 1 over e to the power of x. And again, for completeness, this is the same. This is just negative x. This equals to 1 over e to the x, etc. And this one here, that's just e to the negative x squared equals to 1 over e to the x squared. It's just easier to describe and analyze this way. So this function is greater than this one for this domain 0 is less than x, less than 1, and that's because, alright, because what we have is e to the x squared is going to be less than e to the x in this region. And the reason this is because you're squaring a fraction that's less than 1, and that ends up being, yes, smaller than the exact number itself. For example, let's just go, for example, if we were to just illustrate this even further. For example, if we had e to the power of, let's say, 0.5, so x is between 0 and 1, squared, what we have in this case, this 0.5 squared is equal to, yes, equal to, when you square this, that's just 0.25. And this 0.25, well, this is obviously going to be less than, less than e to the 0.5. So that's clearly less because it's you're raising it to a smaller power. And then when you flip it here, 1 divided by e to the x squared, then you're dividing it by a smaller number, so you're going to get bigger than this other one right here. So also, just one more note on an easy way of thinking about this 0.5 squared, why there's the decimal place over there. 0.5 squared is equal to, well, 0.5 times it by 0.5, which is the same thing as writing 0.5 times 1/2. So the reason squaring it when it's between 0 to 1 is smaller than the actual number is, well, a good way to think about it is think of, or basically think, it's calculating this as half of 0.5, so that's just 1/2 is equal to is 0.25. So this is just so half of it is equal to 0.25. So that's pretty much what we're doing when we're squaring a fraction that is between 0 and 1. And then obviously the opposite is the case when you're greater than 1 in this case. So for x is greater than 1, what we actually have now is the opposite case, and that is basically 1 over e to the x squared is going to be less than, so it's going to be less than 1 over e to the x. And the reason for this is because, again, because e to the x squared is greater than e to the x. So it's the opposite as the previous case I just went over. And again, for example, right here, i.e., what we have e to the, let's say you had a number bigger than 1, e to the 2 right here squared. So at x equals to 2, there's 2 squared, this equals to e to the 4. So when it's greater than 2, when you're squaring it, it's becoming bigger value. And this e to the power of 4 is obviously greater than e to the 2. And if it's greater than e to the 2, then when you're dividing by it, you're going to get a smaller number. And you could also, well, for example, you could just divide both of these by common denominator e squared, e4, e squared, e4, then it cancels out. What we end up getting is basically this e to the 4 cancels, so 1 over e squared, it's greater than, this cancels, 1 over e to the 4. So you can even just do it that route, and at the same, and you're always going to get the same thing as before. So in this case, again, this function is bigger than this function for x is greater than 1. So when you graph this, when you graph it, and again, I did that just to clear up how the graph will look like, and also because it's pretty useful to understand how these, when you're dealing with fractions of powers, etc., and how it's bigger when x is a whole number greater than 1, or any number greater than 1, but it's smaller when you have it between 0 and 1. So if we were to graph this out, what we end up having is, at this point here is 1, so that's both the values go there, and then at the value 1 here, we get the number, well, let's say 1 over e. E is about 2.68, so it's going to be a bit less than 0.5 there. So this is 1 over e, so it's this point. So this function here, the one is going to look something like this actually. It's going to be like a curved like that. And this one is the y equals 2 e to the negative x squared. And now the function, again as this equals, again, to make it easier to look at, 1 over e to the x squared. As you go to infinity, it's going to 0. And now if we were to graph the other one is just going to go smaller and smaller right away. There's no squared factor. But then, as you can see here, it's greater than at this point here. And this function is y equals 2 e to the negative x, which equals to 1 over e to the x. And now this graph basically represents what I just pointed out here. So when x is greater than 1, this function here that we are trying to find integral of is less than this one. So this 1 divided by ex is greater, but then in between here it's going to be less on this side. So what that means is, first we could rewrite the function we're trying to integrate such that we can incorporate these two intervals right here. So the integral from 0 to infinity of e to the negative x squared dx is equal to the integral from 0 to 1 of e to the negative x squared dx, and then plus the integral from 1 to infinity of e to the negative x squared dx. So now we have two integrals right here. This first one, this is just a, I'll just write here, this is just a regular definite integral. It's not improper, it's just integral from 0 to 1, so there's no infinity, and this is a continuous function, definite integral. So it's a continuous function on this range, so that this one, well, obviously converges. There's no need to converge, there's no infinity. So this is regular definite integral, so this has a value. So now we don't need to consider it. So now we just have to deal with this part 2. So now this one right here, we can compare, for this one, we can apply the comparison test. Comparison test or comparison theorem, which I went over in my last video. So we can apply the comparison theorem with the function that we know how to do the integral of, which is integral from 1 to infinity of e to the negative x dx. So we could just apply it, apply the comparison theorem with this one. So what we're doing is comparing with the value if we can solve this, or if this is divergent or convergent. So again, this function, like I've always covered before, this is just a type 1 improper integral. And this just means there's an infinite interval from 1 now to infinity. That's infinite integral right there. So that's just infinite interval right there. And so what we have to do is write it as a limit of a definite integral. So what we could do is now limit from 1 to infinity, 1 to infinity of e to the negative x dx. So this is the function we're comparing it with. This equals to the limit as t approaches infinity of 1 to t e to the negative x dx right here. So now we have a definite integral right here. We could solve this. This equals to limit as t goes to infinity, and now the integral of e to the negative x, that is just, well, e to the negative x, and then you have to apply that negative sign, so it's going to be negative e to the power of x. So this equals to e, so that's the integral. So integral of e to the negative x is itself, but then we're using that chain rule later, so the negative has to go down. So, and now you evaluate it from 1 to t. And then now we gotta evaluate, plug those in. So the limit as t approaches infinity of, now when you plug that in, negative e to the negative t subtracted by, and then when you put the 1, there's a negative already there, so we just put a positive e to the negative t. Just rearrange this, make it a bit neater. This equals to limit t approaches infinity, flip this down, 1 over e, and then minus, flip that down to 1 over e to the t. So when you're approaching infinity on this case, this is going to 0, because now this is going to be 1 divided by infinity. So you're approaching 0, so it converges into 1 over e. Thus we could apply the comparison theorem. So basically, since we know that this one is now, also right here, converges to a value, since the integral from 1 to infinity of e to the negative x dx converges, so we converges and we get a finite value or finite area under the curve. So since it converges, and and here actually, since it converges and we have the function e to the negative x is going to be, well, greater than or equal to negative e to the negative x squared. So it's always greater than equal to it for the domain x is greater than equal to 1. So for this interval, this value is always greater than this one, but since this converges, thus basically, or then, integral from 1 to infinity e to the negative x squared dx also converges. Also converges. So since this converges, so this integral from 1 to infinity converges, and we know that the first one is just a regular definite integral, so that has value. So we're basically this value plus another convergent value. Thus we can say, thus the overall function integral from 0 to infinity of e to the negative x dx is convergent. So we don't need to solve what the value is, but we know that it is convergent. And now I'm going to go over some important and very interesting notes on this particular example. Basically, in this example, we were able to show that the integral from 0 to infinity of e to the negative x squared dx is convergent without even computing its value. In probability theory, it is important to know the exact value of this integral, as I will show in my later videos, so stay tuned for those probability theory videos. And also using multivariable calculus, which I'll show in further down the road as well, it can be shown that the exact value of this integral of 0 to infinity e to negative x squared dx is in fact equal to square root pi divided by 2, which is roughly equal to, this exact value, well, it's roughly equal to 0.8862269255, etc. It keeps going on and on. I just rounded up to the nearest, I just rounded up to a 5 here. So, and again, now, furthermore, the table which comprise of generated values of this integral is illustrated below. I just wrote below there. So basically, this table below, which again comprises the computer generated values of this integral, and the computer probably used Simpson's rule or another approximation method, like I explained in my earlier video. This one is just from my calculus textbook, these values. So again, this illustrates improper integrals quite well. In particular, this improper integral which converges. So basically, from the table, the integral converges very fast to the exact value of square root pi over 2, which when you plug into your calculator, it's roughly equal to that. And this is because e to the power of negative x squared approaches 0 very fast as x approaches infinity. And that's when you look at this table. As you can see, when t equals to 1, you get a sum that's 0.7468, so it's still pretty close to this 8862. And then 2, you get a 0.88, so it's already to the second to 2 decimal places accurate. And then to the t equals to 3, you get up to 4 accuracy. And then you get, from 4, you get to 6 accuracy. And then after the 5, you get pretty much to, this is 6. No, this is 7 actually. 1, 2, 3, 4, 5, 6, 7. 7 plus 3, you get to the 10th digits accuracy. And then 6, as you can see, all you're doing is adding more and more digits further down the road. And this illustrates improper integrals that even though the interval can go to infinity, so as it's going to infinity, all you're really changing is basically all the way down. So what you're actually changing is basically the decimal places are going up higher. So let's say you're increasing the decimal place all the way further down to infinity, so you're not actually changing the value. And in fact, all it is getting closer and closer to this square root pi over 2 value, which this is infinite as well, infinitely long. Infinite in terms of decimal spaces that keep going on and on and on. So that's pretty much why it converges, even though the region is infinite. Anyways, that's all for today. Hopefully you learned from this pretty extensive example on this integral, this non-elementary function, and you can learn more about elementary functions in my earlier video as well. And also hopefully you learned about this, and also I wanted to go in detail about this square root, this power 2 function, or any power function whenever you have a value that you're squaring, or power of 3, etc., when it's less than 1, greater than 0, like something like this, how it becomes smaller. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below, and thanks for watching, and stay tuned for another Math Easy solution.